So let's take a look at explosions. First of all, to make explosions useful, they have to be stable enough for predictable detonation. They create tremendous pressure from their gaseous products, and they have to decompose very rapidly and very exothermically. For more exothermic reactions, the bonds within the compound need to be very weak before decomposition, and after decomposition, they need to form very strong bonds. So let's look at one such compound. Over here, we have C4, which is C3H6, N6, and O6. Below it is also its Lewis dot structure. Next to it is its products, carbon monoxide, nitrogen, and water, also accompanied by the Lewis dot structures. So as you can tell, the chemical equation is currently not balanced. So let's balance it out. So here we have 3 carbons and 1 carbon. So let's add 3 over here. So now our carbons are equal. 3 carbons to 3 carbons. Now we have 4 oxygens and 6 oxygens, and 6 hydrogens and 2 hydrogens. So we can add 3 over here. So now our hydrogens, our oxygens, and our carbons are balanced. We have 6 nitrogens and 2 nitrogens over here, so we can add a 3 right here. Alright, now our chemical equation is balanced. So let's look at our Lewis dot structure. Here we have 1 nitrogen to oxygen bond, another nitrogen to oxygen bond, and another nitrogen to oxygen bond. It should be, yeah, there it is. So we have 3 nitrogen to oxygen bonds. So here we have 1 carbon to hydrogen bond, another carbon to hydrogen bond, another one here, 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 and here. That's 6 carbon to hydrogen bonds. Alright, so let's take a look at our nitrogen to nitrogen bonds. We have 3 nitrogen to nitrogen bonds. Let's look at our nitrogen double bonds to oxygen. 1, 2, and 3. We have 3 double bonds between nitrogen and oxygen there. And we also have carbon to nitrogen bonds here, 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 and here. It's getting a little bit confusing, but there it is. So we have 6 carbon to hydrogen bonds, 3 nitrogen to oxygen bonds, 3 nitrogen to nitrogen bonds, 6 nitrogen to carbon bonds, and 3 double bonds between nitrogen and oxygen. So now let's say we have 1 gram of C4, and we want to know how many kilojoules per mole result from that decomposition of 1 gram of C4. So first of all, let's find its enthalpy per mole. So here we have the enthalpy values for broken bonds and the bonds formed. So here we have carbon to hydrogen. Since we have 6 bonds of carbon to hydrogen, 3 bonds of nitrogen to oxygen, 3 bonds of nitrogen to nitrogen, 6 bonds of carbon to nitrogen, 3 bonds of nitrogen to oxygen, all summed up, minus the 3 bonds of carbon to oxygen, 3 bonds of nitrogen to nitrogen, and 6 bonds of H2O. Now, it should be noted that these 3 bottom ones, the products, were the products over here. And we had, after we balanced it, we had 3 here, 3 here, and 3 here, accompanied by the Lewis dot structures here. Take a look at that. Alright. So I wrote the math here beforehand, worked through it, and resulted in 1,668 kilojoules per mole. That is an enthalpy value for C4. So as I said earlier, how many kilojoules per mole will result from the decomposition of 1 gram of C4? So first of all, we need to, 1 second. we need to convert our grams to moles. So we have 1 gram of C3H6N6O6. We want to convert that to moles. So we use the molar mass of C4, which I found beforehand, 222.11, all over 1, and this is all C4, which resulted in, now we use our previous value that we found for enthalpy, 1,668 kilojoules per mole. Multiply these two, and that will result in oops, wrong paper. There we go. And that will result in 7.509 kilojoules per mole. Alright, on that though, that is an example of a useful explosion, the characteristics of useful explosions, the Lewis dot structures of a useful explosion, and its products, and its kilojoules per mole of a useful explosive. So, thank you.